So a big part of scripting or programming is working with data. That means reading data, manipulating data, and writing back data. So in order to get a grasp of what is possible, let's look at the most basic data types there are in Houdini. Let's start out with a string. And a string just stores a number of text, just a chain of letters. For example, I could store the word entagma in a string, or a name. But more commonly inside of Houdini, strings are used, to example, to point to files, as in this case, where I have a file path stored in a string. The next data type there is an integer. And an integer just stores whole numbers. So the basic numbers that you know from back when you learned to count. And an integer can also store negative numbers, but only whole numbers. You can either store a 1 or a 2, but not, say, 1.5. If you want to store something in between, you need to use a float, which is short for floating point, and is used to store what in math terms is often called real numbers, which also includes values in between those discrete steps that we had from integer, like for example minus 0.77 or 2.41 here. Next, we have two-dimensional vectors, which are mostly used to store x and y coordinates, as in this example, where I have an x value of 1 and a y value of 2.5, yielding a resulting vector that points in this direction. And the way we would write that is with those curly brackets. And we would first write the x component, that is how far we move in the x direction, and then the y component, that is how far we move in the y direction. So this vector would be a vector of 1 and 2.5. And these vector components in Houdini are floats. We can also extend this into 3 dimensions, and it's always a bit hard to display that on a 2-dimensional non-moving screen, but think of it like this. We have our previous vector having an x-coordinate of 1 and a y-coordinate of 2.5, and also we introduce a z-coordinate that goes into the depth and set this to 3. So this resulting vector here is pointing into the depth of the space as well. And the way we write down this vector is with its respective components, the x component first, then the y component, and finally the z component. And again, all of these components are floats. And this is a type of vector we'll be using most commonly in Houdini. Also, there are 4-dimensional vectors, which I won't go into detail quite yet, but keep in mind Houdini supports 2, 3, and 4-dimensional vectors. And usually we use vectors to store positions, or normals, or velocities for particles. So the standard idea is to think of them as arrows pointing in space. However, you can also use vectors to store other 3-component values, such as R, G, and B colors, with the vector's first component storing the red value, the second component storing green value, and the third component storing the blue value. And each of these components, or channels as you'd call them in image processing, usually range from 0 to 1. To get a general feeling for those data types, let's drop down a GeoNode in Houdini, dive in there, delete the file sub, and drop down the rubber toy test geometry. And let's uncheck Add Shader here. So when we middle mouse button on this, we see our geometry has 2 attributes. Normals, as denoted by this capital N, and a position, denoted with this capital P here. So when we go to the geometry spreadsheet that shows the data of this mesh, we see those 7 columns here. And the first column is the point number, and that is an integer, which starts from 0, which is the first point, and goes to the maximum number of points, in our case 12,873. And the point number is stored as an integer as we are counting discrete points, and it wouldn't make sense to have a point 2.5 or 3.5. So we just point them in a natural way that we're all used to. So that's an integer. Next to it we see 3 columns, denoted px, py, and pz. And this is our position vector for each point in the mesh. So that's the way Houdini's geometry spreadsheet displays vectors and the individual components of a vector. So for example, for the first point with the number 0, we have an x position of minus 0.27, a y position of minus 0.0065, and a z position of minus 0.53. Also next to it we have the normal, which is also a vector, and which is the vector pointing away from a surface point perpendicularly. So again, we have the normals x, y, and z component here. Let's head back to our scene and display the normals. So you can see they always point away from the surface perpendicularly. Let's uncheck this and add a color to it. Let's drop down a color sub, wire this up, and set its color to be this blue here. So when we middle mouse button on this, we can now see we added a third vector. And a vector in this window is denoted with 3 FLT, which means 3 floats. So this is a vector 3, the same as the normal and the position. However, it stores the color this time. And by default it is called CD for color diffuse. So let's have a look at this in the geometry spreadsheet here. And we can see we have now 3 additional columns storing the colors R, G, and B value. And you can see they are basically identical for each point in our mesh, because when we look at the mesh, it has a uniform color. So you might ask yourself, if a normal and the color are the same type of data, what happens if we use the normal values to color our mesh? Let's do that and drop down attrib rename sub, wire it up, and let's rename an attribute from N to CD. That's color diffuse, and highlight this. And let me uncheck the lighting here. We can see now our mesh is colored according to the normal values. Let's look at this in the spreadsheet again, and we can see now we have the normal value gone, and instead have our columns for the CD value, the color diffuse value. So what we did here is we just renamed an attribute. So instead of calling our vector N for normal, we call it CD for color diffuse. And Houdini automatically knows what to do with these names and how to interpret them. While on this side in the stream, we added a color value to our geometry stream. So we didn't override our normals or didn't rename our normals, and instead have now 3 attributes. Instead of using a color sub to color our mesh, we could also manually create the attribute named CD and set its value. So let's do that and use an attrib create node here, and we'd like to create an attribute called CD, that's a capital C, and it should be a vector attribute. Let's wire this in here, highlight this attribute create here, and dial in the color by increasing the blue value and the green value respectively. Like so. These are kind of the 3 standard ways how you could create an attribute in Houdini when you'd like to avoid using Vex. However, setting up an attrib create node or an attrib rename or a color sub might be too cumbersome sometimes, and creating an attribute can be really straightforward in code. So let's drop down a point wrangle in our case, wire in our geometry, highlight this point wrangle, and in here we will write @cd equals curly brackets. Let's say it should be 0 in the red channel, 0.45 in the green channel, and 0.9 in the blue channel. And finish this line with a semicolon here. We can see now, in one line, we created the color attribute, and we also set its value. So when we hover over it, we can see now we have this 3rd vector here, denoting the color. And in the geo spreadsheet, we can also see its value here. And of course, I did set the blue to 9 and not 0.9, so let's fix that. Go back to the scene, like so. What you saw me do here is using Houdini's built-in syntax. And the syntax, that means writing an symbol and then an attribute name, allows you to quickly access attributes on the geometry you're running over. In this case, we are running over points, so the syntax will always access point attributes. For example, in addition to this, I can access my point's position by writing capital P, and let's say it should be the current position, plus let's add a vector to it, and let's move it along the x-axis 1 unit, and let's not move it along the y and the z-axis. So we can see now we translated our rubber ducky 1 unit along the x-axis. So this is the quick and, in my case, a bit dirty way of accessing data. Why is it dirty? In this case, everything is fine because I'm reading out a vector or setting a vector, and I'm explicitly specifying that we're dealing with vectors here by using this curly bracket notation. However, you might run into situations where it is not entirely clear what kind of data type you're trying to set here, and Houdini can struggle with that and might end up not setting your data correctly. So, for example, setting only 1 color channel instead of a whole color vector. And to avoid these cases, what I usually do is I explicitly tell Houdini which data type a given attribute is. And the shorthand for this is, if we want to tell Houdini that this data type is a vector with 3 components, we just put a V in front of our @. Same works for the position, which is also a vector with 3 components, so let's do that. And we can see nothing changed here. And I will give you examples where it's important to use the syntax when we will be talking about variables. So what else can we create? Well, we can create integers by dropping down an I in front of our symbol, and then let's call this one testInt, and let's set it to 12. Always finish a line of code with a semicolon, and let's go to the geo spreadsheet and have a look at our attribute that we just created. And we can see now we created this integer storing 12, and it's called testInt. Let's create a float with an F in front of our syntax. Let's call it testFloat, and let's set it to 12.71. Finish the line with a semicolon. And we now have our testFloat attribute in here as well. So this is how setting attributes work. And reading attributes works in the same manner. In fact, we already used it up here. So let's use our test integer here, our testInt, and let's write in our point number in here. The point number, this here, is a built-in attribute in Houdini. It is called ptnum. And if we want to be super clean, let's explicitly specify that this is an integer as well. So we can see now our testInt here contains the same value as our point number here. So that's how we we read out values. And the most annoying or confusing thing, at least for me when I started writing VEX, was how on earth do you know what those attributes are called? I mean, finding out what color is called can be done by dropping down a color sub and middle mouse over this, and you can see color is called CD. But how are you going to figure out that the point number is stored in a variable called ptnum? And this is where a whole other topic of this course begins, coping with Houdini's documentation. So when you click on that question mark here, Help browser opens up and it loads the documentation for the given SOP. And you can see a whole bunch of text here describing what each of the options in the SOP does. But what we're really interested here is a bit hidden. So what I'm going to search for is for VEX expressions. And I'm going to go to using these VEX expressions here, which is just a really quick and broad overview of what VEX can do. And when we scroll down here, we find this paragraph, accessing geometry attributes. That's what we're doing currently. And we find a list of examples that contain most built-in attributes that Houdini uses and evaluates. Also, another and maybe quicker way of finding out how those built-in attributes are called is by going to your geometry and dropping down a point VOP in our case and diving in there. And what you see here in this node, the geometry VOP global, are the names of the most commonly used built-in attribute names in Houdini. So for example, our P for position, V for velocity, and down here also our ptnum for our point number. And when I hover over it, it also shows a tooltip telling me that this ptnum is an integer. And I'm aware that the documentation might not be perfect in this regard, and it might be a bit annoying to drop down a point VOP or primitive VOP each time you want to look an attribute's name. So I've attached a list that we compiled where we collected the attribute names and their types of the most commonly used built-in attributes in Houdini. So let's go up one level again, delete this here. Go to our scene view, and instead of our rubber toy here, let's drop down a grid, scale it to be 2 by 2. Let's highlight it, drop down an add SOP here, and set it up to delete the geometry, but keep the points. So we have now this grid of points here. And now let's get this rubber toy here, move it over there, and also drop down a copy to point SOP. Wire in the rubber toy here, and our grid points in here and highlight it. And we can see now we are generating copies of our rubber toy on the grid. And the neat thing about the copy to point SOP is that by default it is set up to read certain attributes on our points that come in here that are going to dictate how to transform the geometry that comes in here. In essence, how to modify your copies. So let's drop down a point wrangle again, and let's write an attribute on these points coming in here, because currently when we hover over them, they only have a p-value for their position, which is a vector. But let's introduce another attribute, and it's going to be a float. Let's call it p-scale. And I suspect that is short for particle scale. Currently we see our rubber toy is way too big. So let's use the p-scale, which is a built-in attribute that the copy to point SOP will read and use to scale the copies. Let's use that to scale down our rubber toy. So let's set it to say 0.1 and finish it off with this semicolon. And we can see now, let's disable the point display here. We have our rubber toy copied and each of the copies was scaled down. So this would be the same as disabling this node and globally scaling down our rubber toy to say 0.1. Like this. However, the real power of VEX and of this technique comes in when you're able to set each point's scale value individually. So for example, let's try and set the point scale value to our current point number, and that's an integer, and let's reactivate this node. And I think I need to zoom out a bit, because now I can see, depending on the point number, my rubber toy gets scaled up. And I think when I go on the grid, I have 10 by 10 points, that means 100. So in essence, what I'm doing here is for the first point, which has a point number of 0, I'm setting the scale value for my rubber toy to 0. And for my last point, which should have the point number 99, because we're starting to count from 0, my p-scale value is now 99. And my rubber toy is scaled 99 times its original size. Let's have a look at this in the geometry spreadsheet. We can see now here for the first point with the point number 0, my p-scale value is 0. Let's scroll down here. And yeah, for the final point with a point number of 99, we also have a p-scale value of 99 here. So to recap this lesson, there are several data types which are commonly used in Houdini. For now, we looked at the data types string, which stores a text, integer, which stores whole numbers, float, which stores floating point values, and vectors, which can be 2-dimensional, 3-dimensional, or even 4-dimensional, and can be used to store a position, a normal, a velocity, or a color. Also, we looked at how to access attributes using the at syntax, and how to explicitly tell Houdini which data type a given attribute contains, using this shorthand to specify if my attribute is a float or an integer. And finally, we learned that Houdini has lots of built-in attributes that it will automatically evaluate if it finds this attribute on your geometry and if it has the right name, as for example, CD for the color, p-scale for the uniform scaling of a particle or a copy, or pt_num for the current point number. So until next time, it is your task to experiment with this copy-to-point setup a bit and find out which kind of effects you can produce using this really basic technique. However, to make this technique really useful, we have to talk about another concept, that is variables, and we'll do that in the next tutorial. See you then.